When you plug your phone charger into the wall, what do you picture? You probably think of electricity just flowing, right? A simple, straight line of power. But the truth is, what's happening inside that cord is way more fascinating. The alternating current, or AC, that powers pretty much everything isn't a steady river at all. Nope. It's a high-speed, perfectly choreographed dance. So today, let's pull back the curtain and watch this unseen dance of energy.
Here's how we're going to break it down. First, we'll see exactly how AC is so different from the simple electricity in a battery. Then, we'll get into the rhythm and the steps of this electrical dance. We'll meet its key partners, learn the special language engineers use to describe it, and finally, we'll see this all come together in a real-world device you've definitely used.
All right, so let's start with the basics. What really makes this dance so different from, say, the juice you get out of a AA battery?
Well, on one hand, you have direct current, DC. That's your battery power. It's predictable, a steady one-way flow, just like a river flowing in one direction. But on the other hand, you've got alternating current, AC, the stuff in your walls. This is no river. It's a constant, high-speed, back-and-forth motion, a push and pull of electrons in a perfect rhythm. It's a dance.
And this is what that dance looks like on paper. It's called a sine wave. You can see how it smoothly rises up to a positive peak, swings back down through the middle, hits a negative peak, and then comes right back to the start. That whole up and down sequence, that's one single cycle of the dance.
So now that we can see the basic shape of the dance, let's break down its rhythm. I mean, every dance has rules, right? There's a tempo, there's specific moves, and AC is exactly the same.
First up, we've got amplitude. This is really simple. It's just how high the wave gets, its peak value. In our dance analogy, you can think of amplitude as how big and energetic the moves are. A higher amplitude is like a bigger, more powerful swing.
Next is frequency. This tells us how many of those back and forth cycles we just saw happen every single second. We measure it in hertz, or Hz. So if amplitude is how big the moves are, frequency is the tempo, the speed of the dance. Here in North America, the power in your outlets is dancing at a very quick 60 hertz. That's 60 full cycles every second. Okay, now here's where it gets really cool. Phase. See, you almost never have just one AC wave in a circuit. You usually have a few dancing at once, and their timing relative to each other is absolutely critical. Are they stepping in perfect time, or is one a little ahead of the other? That timing relationship, that's called phase. And this idea of timing leads us to something called a phase shift. Look at the two runners. If a wave starts its cycle just a little bit earlier, like the blue runner, we say it's leading. If it starts a bit later, like the red one, we say it's lagging. And this isn't just a minor detail. This little difference in timing fundamentally changes how all the parts in a circuit work together. So, if phase shifts change how components behave, let's meet the components themselves. Let's meet the dance partners, because in the world of AC electricity, each partner reacts to the rhythm in its own unique way.
First, you've got the easygoing partner, the resistor. This is stuff like the glowing wires in your toaster. For a resistor, the two main dancers, voltage and current, are perfectly in sync. They rise together, they fall together, they are totally in phase. They just follow the music, no questions asked.
But then you have the more, let's call them the creative dance partners, capacitors and inductors. These guys actually change the timing on purpose. In a capacitor, the current always jumps ahead of the voltage. It leads by a perfect 90 degrees. With an inductor, it's the exact opposite. The current always falls behind the voltage. It lags by 90 degrees. They're deliberately messing with the time.
So what is this property that lets them do that? It's called reactance. Now, like regular resistance, it does oppose the flow of current, but it does something more. It's the reason we get that perfect 90-degree phase shift. It's the special move that capacitors and inductors bring to the dance floor.
Okay, so you've got amplitude, you've got frequency, you have partners leading and lagging all over the place. How on earth do engineers keep track of all this? Well, they had to invent a whole new language, a new kind of math, just to map out this complex dance.
And the most important word in this new language is impedance. We use the letter Z for it. You can think of impedance as the total opposition to the current. It cleverly combines the simple, straightforward resistance with that tricky time-shifting reactance all into one single value. It's like the total difficulty score for the entire dance routine. But how do you combine two totally different kinds of opposition? You can't just add them up normally. So engineers use this special graph, the complex plane. Think of it as the dance floor. Simple resistance gets plotted flat on the horizontal line. And that phase-shifting reactance, that gets plotted up and down on the vertical line. This is how you see how they work together. And when you plot those forces on the dance floor, you get this, a phasor diagram. And this thing is incredibly useful. It's like a freeze frame of the entire circuit's performance. You can see the strength and the exact timing of every single part, all in one quick snapshot.
And the really amazing part is we're not throwing out the old rules. You know, a classic rule like Ohm's law, it still works perfectly fine. It just gets a little upgrade for AC. Instead of simple resistance, we use the total impedance. And we just have to remember that all these things, voltage, current, and impedance, now have both a size and a direction, or phase.
Okay, this is all fantastic in theory, right? But where does this unseen dance actually show up in the real world? Let's look at a super common and really clever example, the crossover circuit inside a good loudspeaker.
So here's a pretty typical crossover circuit. Any decent speaker has different drivers for different sounds. A big cone, the woofer for bass, and a tiny one, the tweeter for the high notes. This little circuit's only job is to be a traffic cop, and it uses the unique phase-shifting dance of capacitors and inductors to send the right musical notes to the right speaker.
The goal here is really simple. We want the deep, low-frequency boom from a bass guitar to go only to the big woofer. And we want the crisp, high-frequency tss from a cymbal to go only to the little tweeter. If they get mixed up, your music sounds muddy and just bad.
And check this out. This graph shows what the tweeter is getting. You can see on the left, where the frequencies are low, the signal is basically zero. It's blocked. But as the frequency gets higher, the circuit lets more and more of the signal pass through. It's perfect. The components are using their unique dance moves to act like bouncers at a club, only letting the high-frequency notes get inside.
So, the key takeaway is this. The next time you plug anything in, just remember that you're tapping into this incredibly complex, hidden dance. But it's not chaos. It follows very specific rules of rhythm and timing. And by understanding those rules, engineers can harness that dance to build pretty much all of the technology that makes our modern lives possible.
This whole invisible ballet is happening trillions of times a second, all around us, and we never even notice. It really makes you wonder, doesn't it? What other elegant, complex systems are hiding just beneath the surface of our everyday lives, just waiting for us to see them?